Graphs are among the most important mathematical tools. With the help of graphs, even the most complex relationships can be easily described and analyzed. In this episode, you will discover how graphs are present in your daily life and how graph theory is based on simple mathematical foundations. Have you ever heard of artificial intelligence or machine learning? Did you know that technologies like neural networks are actually based on graphs? In these graphs, nodes and connections hold the answers. For example, a well-designed network can recognize a picture of a dog, but if you replace the picture with one of a cat, it will immediately identify that it's a cat. This would be unimaginable without graph theory. But graphs are not only present in artificial intelligence. The social media network can also be represented as a graph. The nodes represent people, while the edges show who is friends with or follows whom. These graphs help us understand how information, trends, or even a viral post spreads. You encounter graphs while using your phone, even if you don't realize it. When traveling, your device always connects to the nearest cell tower, and the connection continuously changes. This is also a graph, where the cell towers are the nodes, and the connections are the edges. The same principle applies to GPS, which models the connections between satellites and the receiver as a graph. This also includes route planning, network optimization, and even the spread of viruses. Now, let's move on to the basic concepts of graphs. A graph consists of points, called vertices, which are connected by edges. An edge represents a connection between two vertices. Graphs can be directed, where the edges have a direction, or undirected, where the direction does not matter. If there are multiple connections between two vertices, these are called parallel edges. If a vertex connects to itself, it is called a loop edge. These basic elements form the structure of a graph. If a graph has no parallel edges or loop edges, it is called a simple graph. And what is a complete graph? We talk about a complete graph when every vertex is connected to every other vertex. Imagine there are 5 people, and each one shakes hands with all the others. This is exactly a complete graph. The number of edges in a complete graph is obtained by connecting n vertices with n-1 edges, but each edge is counted twice because it connects both vertices. Therefore, we divide the number by 2. A graph is connected if it is possible to reach any vertex from any other vertex, even by traversing multiple edges. This means there are no isolated parts, and the graph behaves as a single unit. Here is an example of a graph that is not connected. It is clearly visible that there are vertices that are isolated, making it impossible to reach other parts of the graph from them. There is also the concept of a complement in the case of graphs. The complement of a graph contains the same vertices as the original graph, but it displays the connections that are missing in the original graph. Simply put, we look at which vertices are not connected in the original graph, and we add edges between them. The complement graph, therefore, represents the missing connections of the original graph. In graphs, a fundamental concept is a walk. Of course, we don't mean it literally. The walk describes the movement between the vertices and edges of the graph. A walk always has a starting point and an end point. We start at the starting point, follow the edges, and move from vertex to vertex until we reach the end point. In a walk, vertices and edges can be repeated, and the length of the walk is determined by the number of edges traversed. Imagine a delivery company transporting packages between cities. The delivery driver's goal is to complete the delivery using as little fuel as possible. So, they need to find the fastest and shortest route. In fact, they need to optimize their walk in the graph. There are several special types of walks. For example, if no edge is repeated during a walk, it is called a simple walk. Consider the walk A, B, E, D, B. This is a simple walk because no edge appears twice. If we can connect the vertices in a circle in a graph, then we are capable of a cycle walk. This is a walk where the starting point and end point are the same. Imagine that we follow the path A, B, D, E, A, and then start the same circle again. If, during the walk, each vertex is touched only once, it is called a path. For example, the walk A, B, D, E is a path because there are no repeated vertices in it. A circuit is a special type of cycle in which each vertex and edge is touched at most once. For example, the path A, B, D, E, A is such a circuit. Remember, during a cycle, we can make multiple loops, but in the case of a circuit, only one. And now, here come the special cases. If a path touches every vertex of the graph, it is called a Hamiltonian path. This is a real challenge, as we must visit each vertex exactly once. If a cycle touches every vertex of the graph, it is called a Hamiltonian cycle. This is also an interesting problem, especially in the case of larger graphs. Another special type of graph is a tree. We call a graph a tree if it is connected and acyclic. The structure of trees is simple, but they have a very important rule. If a tree has n vertices, it always has n-1 edges. The arrangement of the graph's vertices is arbitrary. The connections between the vertices must remain intact. If there is a graph where the edge connections are the same, but the arrangement of the vertices is different, it is called an isomorphic graph. Let's continue with the properties of graphs. The degree of a vertex is defined as the number of edges that connect to the given vertex. This can be determined very simply. We just need to count how many edges are connected to the given vertex. Now let's examine an interesting statement. We say that in every finite graph, there are definitely two vertices that have the same degree. How can we prove this? Let's approach the problem indirectly, meaning we will try to assume that the degree of each vertex is different. Let's start by drawing the vertices. We have a vertex with degree 0, that is, a vertex that has no edges connected to it. Next, let's take a 1-degree vertex, then a 2-degree vertex, and so on. We assume that the degrees of the vertices are different, but our graph contains a finite number of vertices. If we reach a vertex with a degree of 3, we must connect it to every other vertex to satisfy the condition. But here's the problem: if we connect the vertex with degree 3 to every other vertex, the 0-degree vertex's degree will increase by 1, and so we will no longer have a 0-degree vertex. The 1-degree vertex will become 2, and so on. Finally, we see that two vertices will have the same degree, as we can see that we end up with two vertices with a degree of 2. This contradicts our assumption. Therefore, we have proven that in finite graphs, there are always two vertices with the same degree. But what about infinite graphs? Here, the rule no longer applies. If we have an infinite number of vertices, we can draw a graph in which every vertex has a different degree. This case arises from the special properties of infinite possibilities. This is an illustrative example of how finite and infinite structures can behave so differently. Let's look at our final challenge. We are in the city of Königsberg, where 7 bridges are located. Our task is to walk through all the bridges of the city exactly once. The problem can be represented as a graph. Let's give the walk a try. Let's start from the island, that is, from vertex A. Let's cross to the southern side and back. Then to the northern side and back. 4 bridges done. Let's head east, then south. Oh, we've been here already. This didn't work. Let's look at the degrees of the graph. We can see that every degree is odd. The famous mathematician Euler realized that if the degree of every vertex in the graph is odd, then there is no path in the graph where each edge is touched exactly once. If the degree of every vertex were even, we could walk around the bridges in a cycle. If there were at most 2 vertices with odd degrees, we could still go through all the edges, but our starting and ending points would be different. Let's play a game. Try to draw a figure between a few points, such that you must touch all the points, you cannot lift your pencil, and you can only cross each edge once. These are called single-line drawings. Picasso was one of the great masters of single-line drawings. He imagined the points in his head, figuring out which ones to connect, and then walked the pencil along the graph's vertices. In other words, he drew the Euler path. Can you see that this dog is made from a single line? Thank you for watching the video. If you found it helpful, don't forget to subscribe and like the video too. Be sure to check out the other videos in the course to continue building your knowledge. See you next time.